As ECU technology is becoming more and more advanced, this gives a lot more control to the tuner, and particularly with cars making huge amounts of power, like the open class cars at World Time Attack, controlling the power delivery to the racetrack is key. And we're here with Brad Sheriff from Racetech Performance to talk about Motec's M150 platform, and in particular a torque-based ECU model. So, Brad, we hear this term thrown around a lot, torque-based control. What's it mean, and what does that give you as a tuner in terms of control?
Okay, I guess going back some time ago, I purchased a cylinder pressure scope, and it was very interesting and an important part of the learning base that we understood what was happening inside the cylinder. And very quickly we worked out that the cylinder pressure had a big relationship with torque. So we started torque mapping engines using boost pressure and not so much ignition timing to limit those values, to try to keep the cylinder heads on things prior to billet engines. And it's always been a bit of an issue with RBs, trying to seal the engines up over a certain cylinder pressure or torque value.
So essentially you're talking there about purposely holding the boost pressure a little bit lower through the peak torque area of the torque curve in order to limit and control cylinder pressure?
Yeah, exactly. I mean, when boost control, when we first started to play with this, the first thing to do was pull off the electronic control and put a boost tee on. Very quickly we worked out that was probably not the effective way to control the engine. And in conjunction with using the pressure cylinder scope and boost pressure, we were able to hold that torque figure flat. Now that was quite a bit more difficult than the options that we have now with this new package, but it was very effective, and it wasn't uncommon when we were sneaking into compression ratios north of 11:1. That we were running, say for instance, 22, 23 pounder boost at 4800 to make the targeted torque, and 55 pounder boost if the turbocharger was efficient enough and the exhaust back pressure was still around, no greater than 1.3 to 1, to maintain that torque all the way through to where we wanted to use the engine, so 995.
Okay, now you just introduced a term there which I just wanted to clarify a little bit for the viewers who maybe aren't familiar with the Motec product, which we're specifically talking about in this chat. You said a package, which is a firmware package. So just to clarify there, the Motec M150 ECU is really just an electronic box, and what it can and can't do is really completely dependent on the firmware. So we're talking here about a new firmware package which is torque based. So I just wanted to get that out of the way so those who maybe aren't familiar just have a bit of understanding. So what you were talking about there with the scope, that's a fair while back. Things have come a long way since then. So talk to us about what is included in this new torque based package that you've been developing with Motec, and what does that give you in terms of control?
Well, the torque based package came about through many discussions about the need for a better traction control system. Darren Reynolds from Motec's an extremely clever guy, and Phil Morris put me in touch with Darren, and together we bounced some ideas around. My idea originally wasn't probably to use the torque model, but once we started to tip the ideas together, it certainly made sense to go that way. It's given us the ability to map the engine using a torque target. So we're able to, once the throttle area is set, we're able to put an engine on the dyno. If we've got some relatively close ignition numbers, it's all about having the ignition timing table mapped to MBT, or very close to it, because it's impossible for the ECU to work out, if we yank 10 degrees of ignition timing out, the torque value the engine's making. It's an unmeasurable value, so there's a little bit of work in that, but once that's set up, we are able to run the engine. If we select 400 Nm, for instance, it will make 400 Newton meters at the earliest point that the engine's mechanically able to make that, and it'll hang on to it until we're out of turbocharger effectively. So we set a value that we're allow it to the maximum boost pressure it can use at a given RPM. Now that won't be a flat line, it never will be, but it may be 25 pounder booster, for instance, if we were trying to make 1100 Newton meters at 4500, and that if it needed the range and the turbocharger was capable to work at a pressure ratio of, say for instance, 50 pounder boost at 10,000, The ECU will use everything you've given it, so the maximum amount of timing in the table plus or minus compensations. It'll use the maximum boost pressure you've told it it's allowed to use. The big advantage here is we also pick up the ability of the waist throttle mapping. So the engine, once it actually becomes boosted, the M1 will wind the throttle back to effectively the minimum amount of throttle to make the targeted torque. So that means from the driver's perspective, if he comes off the throttle pedal by 10% and we're making 1,000 Newton meters, we're going to expect as a driver a reduction of 10% of torque. So from an analog position from the driver, it's a lot nicer thing to operate.
All right, so let's dive into that. We've gone pretty deep down this rabbit hole pretty quickly, and I don't want to lose our viewers. So let's just come back a couple of steps. If we think about a conventional throttle system, let's go even cable throttle with a turbocharged engine, and we go to wide open throttle and we get X amount of boost. Let's say that's 30 psi.
Yep.
And the problem is that when the driver's at wide open throttle and wants to reduce torque, obviously we reduce the throttle position. But when we reduce the throttle position from 100% to, let's say, 90 or even 80, really the turbo is so good at making boost that it'll probably still stay at or very close to 30 psi, and we may not actually see any reduction in torque. So it's not until the driver actually gets back to maybe 50 or 60% or maybe even less that we actually start to see a noticeable drop off in torque. And that in turn makes it very difficult for the driver to modulate throttle position and get a sort of a relevant reduction in torque, correct?
100%. The throttle's more like a digital input than an analog. So we've been mapping for some time waist throttle. I've always been big on that idea. Big power, especially rear-wheel drive cars. We'd map the engine and just say it made 1,000 horsepower at 100% throttle. We'd then map it back. Normally you'd knock 10% out of the next run, and you'd find that it'd make the exact same power once it had boost pressure, all the way up to probably 9,000 RPM, and you'd see another maybe 10 to 20 horsepower again at the top with the extra 10%, but only over 9,000. So that would mean then we'd only ask for the last 10% of throttle over 9, and then we'd work backwards from there. What we found fairly rapidly was if we were to use that model and build a table, and we didn't treat the engine as an aspirated engine before it had boost pressure, so it required 100% throttle while the engine was still atmospheric or building boost, the engine was very slow to build boost. So it was a little tricky. So this particular torque package uses the conventional 100% of throttle whilst we're building the targeted torque. Once it's then approached that target torque value, we target a margin between or pre and post throttle, and we're always looking to maintain that boost margin.
So you're talking a boost margin across the throttle body, so you're looking for a differential pressure there.
Differential pressure. So the ECU, you could have 70 kPa if you wanted to do that, but 20 kPa is a good working value. So it's not uncommon, for instance, for this engine that's making 1,250 odd horsepower at the hubs, not to exceed on a dry-by-wire throttle on an LS90, not to exceed 50 to 60% of throttle once it's actually up and going down the main straight, and to make the 1,100 Newton meters that we're targeting. Now, obviously, at the back side of the track where Tim picks the throttle up, it'll go to 100% throttle. The moment that it's making the targeted torque, the throttle will be then closed back. He'll still be at 100% pedal, and then we'll maintain that minimum throttle with the 20 kPa margin unless the torque target changed.
Okay, so I think probably viewers at this stage might want to rewind a minute or so and just listen through that, because essentially what you've just said there really will probably fly completely in the face of conventional thought process that if we want maximum power, we need maximum throttle, correct?
Yeah, certainly, and this probably goes back to carburetor days. If you wanted to run, you wanted to make a big number, you put the biggest carburetor, and if you couldn't get a big enough carburetor, you put 2, and if you could fit 3, you put 3. These days, they were all aspirated engines, and if you look at the efficiency of the engines now, the efficiency of the turbochargers, then and the size of the throttle bodies, that's the other thing. I don't know if you remember back when I was little, an XF throttle body was large, and I think they were like 70 odd mil. Now we're talking about an off-the-shelf throttle of 90 mil off an LS. We tend to use the LS a fair bit. I like the digressive opening on the LS. The Bosch throttles are fine too. We find that even on the Hammerhead, it's got one of the smaller Bosch throttle bodies on it, and very rarely to make 1,050 hub horsepower, that the throttle on that car, once it becomes pressurised, will exceed 55%.
All right. I think we've probably discussed that element of this package in enough detail to move on. Now, obviously, the more complicated a package becomes and the more control functions are in there, one of the balances that we need to keep in mind is, are we making it so complicated that a tuner can't provide all of the information that's required? And what we haven't talked about so far is some of the more advanced concepts, such as modelling how much traction is actually available based on lateral and longitudinal G-force, downforce, etc. So is there a balance you have to keep in mind there so that it can actually be tuned and you don't need to have a PhD in order to be able to put a map in a car?
Sure. What we've maintained is that we wanted to be able to migrate a general purpose package across from Motec. So if someone can tune Motec M1, you're able to migrate all of those values over. So we're talking about
fuel and VE.
100%. And same with boost pressure. So
Ignition and VE, I should say.
Yep, 100%. Well, there'd be 80% of your package that will come across. So that part of it, you could plug those numbers into an engine, start the engine, and you could then, within one run on the dyno, screw that torque value to 500 Newton meters, and you would achieve that. Now, there are a few things that are extras as we discussed. And now, whether you wish to tune those or whether you wish to wind the traction model right up out of the equation and say, well, I don't want to use our traction model, which is our predictive value taking downforce, centre of gravity, etc. That's completely up to the tuner. But and the other thing too, from our perspective, when I say our Motec, we want to be able to supply this package with some really, really good numbers that are usable. Now, they may not be right, 100% right, but as Murray Coote would say, they're 80% right and 20% not wrong. So this is something that we work on a lot, is that we have to have the whole car 80% right, and those numbers that would be in there, if you were out by your centre of gravity by 1.5 inches, trust me, there's many things in the car that you'd probably want to concentrate on before you're worried about that.
All right, so just to paraphrase there, the actual tuning process with this torque-based model is no different to a conventional Motec GPRP, and then the torque targeting is over and above, and you don't need to use any of the other trickier stuff, which we're going to dive into if you don't want to.
Look, no, you definitely don't. The only thing we need to tune that's additional is our throttle area table. Now, our throttle area table is very basic to tune. It probably would take you somewhere between, it's a static loaded value. It'd probably take you somewhere around 5 to 8 minutes to set that as a separate tuning tool. And it's as simple as literally holding the engine at a given amount of load and queuing it, and then going to the next load site, queuing it. There's no rocket science in it.
And just for those who are non-Motec, when you say queuing it, the Q key is basically an auto tune for some of the tables.
Yep, and there may be a couple of places, if you were to start on the throttle area table 3/4 of the way up, the numbers must run in a linear fashion upwards, and you may have to go back and touch a couple of the lower sites up. But look, the other thing we're going to do is be able to supply a table, and I guess depending on who you buy the package from and how much support you want, if you say, look, I've got a 90mm Bosch throttle body, LS throttle body, it's non-modified, I've got a 72mm Bosch, we can supply you those area tables.
All right, now let's get into the sort of the nuts and bolts of why this is all valuable, though, which really comes down to what the tyre can actually put to the track. So this is really the whole reason for incorporating this advanced torque model, is that as the car goes around the track, the amount of torque that can be transferred to the tyre is going to depend on a number of things. The gear ratio is obviously going to be a big impact because that's a multiplier of our engine torque. Then we've got the speed of the car, because with downforce we get more traction as the car goes faster, but then as we go around a corner and lateral G-force increases, that also affects things. So can you talk to us a little bit about how all of that modelling works and how you incorporate that?
Okay, so basically we input the weight of the car. We work out a value that we think, if you don't have shock potentiometers, and a lot of guys won't have that, we'll take a stab at what the downforce values will be. Now, once again, we've got to be 80% right, 20% not wrong. And if we are on the low side of the downforce figures, it will just mean that our open loop strategy for how much torque we think the tyre can cope with might be a little low. But the package broadcasts the actual downforce value, so we're able to view that in the logging, how much downforce we're making. And you'd come up with a figure. Most people would be able to look at a vehicle, and if you were saying that a supercar makes 350 kilos at 200 k's an hour, they say, well, I've got a supercar wing and I don't have as much front end, and let's just call it 200. If you didn't have a downforce figure in there, sure, we wouldn't be as accurate with our prediction, but as a driver, there's a whole heap of other ways to calculate that. We're able to, like you said, with the gear ratios, the biggest common denominator, we know we can do a bigger skid with a little engine in first gear than we can in top gear. There's several things there. The biggest thing is the multiplier of the torque, with it being the gearbox. The aerodynamic downforce increases the amount that the tyre will cope with. The amount of side load we put on the tyre, we know that if we increase the side load by 1G, 2G, 3Gs, it doesn't want to drive the car forward. If we have 100% of available grip in a straight ahead direction at 100 kilometres an hour, if we want to turn the steering wheel 10 degrees, we pull two side Gs, we're going to have to reduce the engine loading on the tyre, otherwise we're going to be going around in circles.
So essentially, putting all that together, what you've got is this, you've got an open loop model of essentially based on speed, cornering, G-force, everything that we've just talked about. This is how much torque we should be able to produce or ask of the engine in order to maintain traction. So that's kind of the gist of it, yes?
And the big thing is we need to be over what the tyre can cope with, right? The traction control, and that's the biggest. This is where this whole package started off. I wanted a better solution for our big power engines. A lot of the cars ran shims. SR20s don't like cut. And I wanted a better traction control system. We had the ability to use a drive-by-wire throttle version of traction control, and we can do that without any type of cut. We can use a cut intervention for the split second that it takes to control the breakout and grab it with the throttle. For instance, the Hammerhead's running no level of cut whatsoever. It's got a reasonable amount of downforce and some engine. And it's converted it from being something that's wild and angry to driving a Magna to the shops, but you're just going quite fast when you're shopping.
So what you're sort of talking about there, just being slightly over the amount of traction, so you can induce some wheel spin if the driver wants. Yeah. But because you're only marginally over the torque that the tyre can put to the track, what that means is when the traction control intervention occurs, we're not requiring an 80% cut, like a really significant event to try and get that traction back. It should be relatively mild.
Yeah, 100%. And obviously that changes with gear and speed like we spoke about, and this is where this open loop model, if you like, is predicting this number. Now, when you say that you have to be a propeller head, and I'm certainly not, to be able to work that out, we want to be above it. Now, for above it by 20%, we're still a mile ahead of where we were when we're above it by 70% when we're in first gear, torque multiplier of 2.5, no downforce, a heap of side G. And now we're delivering 1,000 Newton meters to the tyre multiplied by 2.5, and you can find that you do a lot of circles and you don't get to the destination, and we pull all of that back. So, yeah, like you said, a good driver always wants to do some. The closed loop traction control, it's going to do some, and between the driver and the traction control, the closed loop traction control, we're able to keep it in that check, whether it be 5%, 6%, depending on the tyre, depending on the car, of slip, which is the optimum value to accelerate that car.
I can only assume as well it's easy enough to have a driver rotary switch or something of that nature to overall up and down that open loop torque model.
Yeah, we do that, and I think that whilst you're working through that, not often do you always have a laptop on somebody's knee. So we use a rotary driver switch and we use a coefficient value on that tyre. So with any type of tuning, we can either start at the low end of the scale or the high end of the scale. I've always found, let's throw a whole heap at the tyre. It's very quick to work out that the tyre's got too much. It will certainly, and it's very easy to work out how much traction control intervention we're getting in a percentage of value. So we go, okay, we're over by this, this, and this. We can come back with that. Now, being able to adjust it on the fly, and depending, some drivers don't want to play with that. I tend to want to turn the knobs because there's never enough excitement in going around the corners. So we're able to tune it. So we're above by 10 to 15%. We don't have tyre temperature because it becomes very, very difficult to get an accurate tyre coefficient value with temperature on different tyres. So that would be something you'd have to go to uni for. So we've left that out at this point in time. And to be honest with you, I thought it was going to be a bigger problem than it is, and that isn't an issue. So if we run this over a race distance, we'll actually tune that value back as the tyre goes away. On the warm-up, normally we're trying to work the tyre and the slip value quite hard, so you don't worry about it. You let the tyre shake its head. Once the tyre's up, it's in the happy window. The tyre normally will always go backwards over the length of the race, so we'll ask a little bit less, winding it backwards as we go. The way the traction control, the closed-loop traction is, to be honest with you, the torque model isn't anywhere near as important as what I thought it would be, because it is so effective at controlling the slip within check, but still allowing you to have enough engine to drive it off the outside tyre. And without any cut intervention using throttle, we don't have the issue. Some of these big engines making 12, 13, 1400 horsepower, they'd be on the cut 60% of the lap. The engine wouldn't stay together.
I think that's an important aspect that a lot of people overlook with these high-powered engines is that using a lot of cut can actually damage the engine, so anything we can do to stay away from that, and that's even aside from the engines with shims that can end up getting popped off.
Yep.
Obviously, there's been a lot of information. We've gone pretty deep down this rabbit hole, and this package is clearly not going to be for everyone, but when you're running at an event like World Time Attack with huge power levels, yep, and you are going to be traction limited, getting that dialed in can really make the difference. So thanks for giving us some insight into that, and we certainly look forward to seeing how cars like the Hammerhead go over the course of the weekend.
Sure.
If you like that video, make sure you give it a thumbs up, and if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.